The scientific approach to knowledge is empirical. Empirical is a word that means by experiment. We learn things about atoms and molecules and matter in general based on observation and experiment. And you've probably heard of the scientific method. It's an approach for learning about matter. It's not a set of steps. We do this and this and this and rigid. It's more of an approach to learning about nature. So we observe nature and its behavior, and then we have ideas about those things that we observe, and we do experiments. So key characteristics are observation. Let's write on this, just because we can. So we've got observation, formulation of hypotheses, experimentation, and then we've got formulation of laws and theories. So observations, in science we call those data. Data is plural, one observation is a datum. You rarely hear about those, just one. So data, things that we observe. And descriptions of characteristics of behavior of, that didn't go very well. They're descriptions about the characteristics or behavior of nature. It could be the color of something, it could be how heavy it is, it could be, oh wow, when I lit the match it exploded. Those would all be observations. Some are qualitative, just saying, oh wow, it's green, or some are quantitative and have a number associated with them. So your book kind of gets into this example of Antoine Lavoisier, who lived in France, you kind of guess that from his name, in the 1700s. And one thing that he observed is that when he burned something in a closed container, the mass of the container and its contents didn't change. And so you might say, well, what on earth did he do that for? I don't know. He was curious. So you think, you put a log in the fireplace, right? And if you can actually find a day when it's legal to burn things in your fireplace, you burn the fireplace and you have a nice fire. And when you're done, what's left in the fireplace? Ashes. Do the ashes weigh the same, more, or less than the wood that you stuck in there? Less. They weigh a lot less, right? Did you ever think about what happened to the rest of the mass that was in there? Where'd it go? It went up the chimney. When you burn wood, it mostly makes carbon dioxide and water, and some smoke and some particulate matter, which is why our air is so horrible around here, but the fire is nice, right? So when you burn a log, you expect the mass to get less. He burned something in a closed container and found that the mass of the whole thing didn't change. That was weird. That's not what he expected. So that was an observation. We make an observation and that leads to a hypothesis. Hypothesis is a tentative interpretation or an explanation of the observations. This happened. Why do you think that happened? So he explained this by saying that when a substance burns, it combines with a component of air. He actually called it phlogiston, and he was dead wrong. But, he had this cool observation, and then he made a hypothesis. What's important about a good hypothesis is it has to be falsifiable. It's kind of a funny word, falsifiable. It needs to be something that you could test and possibly prove wrong. Turns out you can't prove things right. You can only prove them wrong. And so all these things that I'm teaching you that we believe to be true, we believe them to be true only because we have no information that contradicts them. But we could come up with examples of things that were believed to be true for a long time until we discovered atoms. And now we know that that's not true anymore because we have a better explanation. So the hypothesis needs to be testable and falsifiable. So we test the hypothesis using an experiment. And an experiment is going to be a very controlled procedure. And we design it in a way to generate certain observations. We kind of go through this process in a very, very informal way in our everyday lives, right? And when you get two nerd chemists in the same house and their children are growing up to be nerd chemists, then you see some interesting things happen. We tend to be a little more controlling about our experiments at home. But, I'm trying to think of an example while I'm blithering here. Pardon me?
Grape in the microwave.
Grape in the microwave. Okay, so that reminds me of something that happened. I've never actually done a grape in the microwave, but that could be fun. So my husband drinks coffee. I don't drink coffee, but I make coffee for him because I love him, right? So I had heated water in a cup because we have this thing, you just heat the water and you pour it through. It's a Chemex coffee filter, and it's really cool. It looks like, anyway, you can look it up. It's very cool. But I boiled water in a cup, and then I got distracted, like I often do, and forgot to pour it through the coffee. So I just stuck the cup of water back in the microwave. And I turned the microwave on, and I'm just like, la, 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 la. And all of a sudden, boom, and the door to the microwave just swings open. And I was just like, wow, what on earth? Because if I had stuck a grape in the microwave or something weird, I might have expected something to happen. Cup of water. Like, what on earth happened? So you could come up with a hypothesis for that and then test it. Ooh, let's see if we can do it again. Although that was kind of scary. I'm not a fan of big, sudden, unexpected noises. But you could test it. You could say, well, gosh, what on earth happened? Maybe I got some special water that it's explosive. There was basically no water left in the cup. The inside of the microwave was wet, and the cup was pretty much empty. So that's an observation, and then you're like, what on earth? So you come up with a hypothesis, and sometimes you kind of come up with an experiment and a hypothesis sort of at the same time. How could I get that to happen again? Well, here, I'll take the same cup and fill it with water and do it again. No, it didn't happen. It was the same cup, right? Okay, so, well, maybe the same water in a different cup, and you start changing things just one thing at a time. That's what controlled means. You don't just kind of randomly do stuff. You do it in a controlled way. You say, I'm going to change this thing, and I'm going to keep the other things the same. So it turns out what happens with the water is when you boil water, water normally has dissolved gases in it, and when you boil the water, those gases come out, the water boils, and then as it cools down, the gases don't go back in there. And if the cup is smooth, there's nothing to generate bubbles when it gets to the boiling point again, and so you can actually superheat the water. It can heat above the boiling point of water until it will suddenly nucleate, and then it will generate one giant bubble of steam, which gives off a lot of pressure, blows the microwave door open, and sprays really hot water all over the place. So don't necessarily advise you to try that one at home. But weird things can happen with microwaves. I'll leave that at that. So we experiment. You'll find that it's very fun to get me off on tangents, by the way. I just do that. Squirrel. So experiments, where am I? Okay, so from the experiment, the results might support the hypothesis. Say, yeah, that hypothesis seems to be good. And we're not going to just stop there. We're going to test it some more. Or may prove that that hypothesis was crazy, right? So if it says the hypothesis is wrong, sometimes we just need to modify the hypothesis a little bit, test it again, and then we're okay. Other times we realize that hypothesis was bad, we just completely discard it. But there's a process that we go through in learning about nature. So then the other two components of the scientific method are laws and theories. So a law is a brief statement that summarizes past observation and predicts future ones. Basically, it's saying what happens. A law tells you what happens. So, you're familiar with the law of gravity. So, if I hold this pen out, what does the law of gravity predict will happen if I let go of it? It'll fall. Every single lecture, every single semester does the same thing. Why does it do that? Well, the law of gravity says it will. Well, that's not a reason why. The law of gravity doesn't explain why things are drawn to the center of the Earth. It just says that they are. In fact, scientists are still kind of arguing about what exactly is gravity. We don't really understand it yet. There's physicists that are trying to figure that out. But the law says what happens. So it is, it's not just one person's observation. These are repeated observations, always seems to follow the same pattern that becomes a law. So from Lavoisier's hypotheses and experiments, he came up with the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. Now, sometimes it went somewhere that you weren't aware of, like when you burn wood in your fireplace. There's water vapor and carbon dioxide that's going up your chimney. It has mass, and that's where most of the mass from the wood is going, and you weren't aware of it happening. But when you do it in a closed container and all of that has to stay, the mass is the same before and after. It's just changed form. The scientific law allows you to predict future observations, so that can be really helpful. Now, state laws, there's a law that says you're not supposed to go above 70 miles an hour on Highway 99. Now, can you violate that law? Sure you can. People do it all the time, right? In fact, sometimes if you don't do that, you're going to get run over or rear-ended. But you can't choose to violate scientific laws. It just works that way, and you can't just not do it. We can't say, well, I'm not going to follow the law of gravity today. Yeah, well, you're going to get hurt, aren't you? So a theory explains why. It not only says, it just doesn't say, nature does this, the pen falls. But the theory explains why it does that. And again, this is not just going to be one person's hypothesis. This is going to be one or more well-established hypotheses that will be brought together as a theory. And, there's no committee that decides, okay, this is a theory, and no, that's just a hypothesis. It kind of just happens on its own. Scientists are very skeptical of each other and curious, and we see somebody publish something that they did this, and they're like, ooh, I want to try it, right? Because we like playing around in the lab, and we like lighting things on fire. So, you do it. You're like, ooh, let me see if I can get the same result that they got. And so you publish a journal article, and then other people try to do the same thing. That's why you put your procedure in there, so someone else can do exactly the same thing. They should get the same outcome. And then that becomes established that, oh yeah, that really works, and this is why, and it's predicting things. Theories predict things as well. So from John Dalton's experiments, Lavoisier's experiments, John Dalton, who lived a little bit later, came up with what's called the atomic theory, and that explained the law of conservation of mass. In it, he proposed that matter is composed of small, indestructible particles called atoms. So the wood, or whatever Lavoisier was burning in that closed container, was composed of atoms. And the reason that the mass didn't change is those atoms are indestructible. They didn't get destroyed or vanish or anything. They just got rearranged into some other stuff. They took the Lego bricks and they built something else out of it. And it turns out some of those things were gases and you couldn't really see them, but they still had mass in the container. That explained the theory. Explained the law. The theory explains the law. The law says this happens, the theory says why. So that's the important distinction between theory and law. Law says this happens, theory says why. And if you have a hard time remembering that, remember the law of gravity. The law of gravity tells us what happens. Laws tell us what. Law of gravity does not tell us why things are drawn to the center of the earth. So theories are validated by experiments. They are explanations. They're just essentially glorified hypotheses. But we can't prove them to be true. We just accept them as true until we have further information that could possibly reveal a flaw or prove them to be incorrect. And John Dalton's atomic theory had a couple of statements in it that were not quite correct. He said that atoms are indestructible. Is it possible to destroy an atom? Absolutely. Nuclear chemistry. You can destroy atoms. And so then the theory has to be revised a little bit. They did not know about that at the time. But theories provide a general explanation for the characteristics and behavior of nature, and they help us to predict what might happen in the future. You try doing something that hasn't been done before. The theory, the explanation for how this thing works, allows you to predict what might happen in the future. So here's kind of a flowchart diagram. Some people like these, some people don't. Here it is, take it or leave it. So we've got observation. Observations can lead to laws. You know, I drop a pen and it falls, and I drop this and it falls, and it always falls the same direction, and all these observations, law of gravity. Observation can lead to a hypothesis. I think this is why this is happening, and then you test it. So you take that hypothesis and you test it with an experiment. And the result of that experiment causes you to either affirm the hypothesis or modify it or discard it. And so we often go around in these loops multiple times. You'll hear me say this in labs sometimes. Chemistry can be tedious. Okay? Science can be very tedious at times. But then there's these bits of really exciting parts too. There are a lot of things in life that are like that. And the law is tested with experiment and then confirmed or revised, and sometimes we go around and around here, and a law can lead to a hypothesis. Remember, the law says this is what happens. The hypothesis is the tentative explanation. A well-developed hypothesis leads to a theory. Theories are also tested. And so we have these testing loops in here. And a lot of times when kids do science projects, they're just repeating some loops here that other people have done. But a well-established theory is as close to truth as you can get in science. And sometimes people say, oh, that's just a theory. No, to a scientist, a theory is a significant thing. That's not just, oh, I think this. That would be a hypothesis. A theory is well established. Multiple people have tested it, and nobody has been able to prove it wrong yet. A theory is very important. You also don't want to have the incorrect assumption that science is a strict set of rules and procedures that's going to automatically lead us to inarguable fact. There is math in science, but science is not like simple arithmetic, where 2 + 2 = 4. It's a lot more complicated and more interesting than that. So here's an example. Which statement best explains the difference between a law and a theory? A law is truth, whereas a theory is a mere speculation. B, a law summarizes a series of related observations, while a theory gives the underlying reasons for them. Or C, a theory describes what nature does, a law describes why nature does it. It's not letting me write B. Okay, so A is just crazy talk. B is correct. What's wrong with C? It's exactly backwards. Okay.